tweets using machine learning and NLP techniques. So the authors of this term paper are Mehanović, Mirza Novalić, Dino, Kečo, Dželila, Mehanović, and myself. We are all coming from the Department of Information Technology of the Faculty of Engineering, Natural and Medical Sciences of International Burch University in Sarajevo and Bosnia and Herzegovina. And we are presenting this term paper at the International Conference on NLP and Machine Learning Trends in Vienna in Austria. So first of all, we are going to go to the table of contents. So what we are going to cover today. So some of the key parts are introduction, literature review, materials and methods with the subsection of data set, data processing and analysis, machine learning model, and at the end we are going to talk about results and discussion and conclusion about this term paper. And this is in general our paper structure. So for the introduction part, we covered the three main topics. So first of all was the sentiment classification. What really sentiment classification is? So it is the analyzing social media opinions and classifying those tweets based on the sentiment. So we classify them as a positive, negative, and neutral using NLP and machine learning. For the natural language processing role, it is the key is to understand words and everything regarding that can help us to classify these sentiments as a positive, negative, or neutral. And we saw that there is a growing demand and the need for this topic, so we decided to do this topic. And it is essential for the businesses, researchers, and individuals to analyze trends and other things. So for the literature review, we did cover 7 term papers, and some of the algorithms that were used by the other authors regarding this topic were naive Bayes, linear support vector classifier, SGD classifier, Bernoulli naive Bayes, logistic regression, multinomial naive Bayes, passive aggressive classifier, and perceptron. And later on, we used also some of these algorithms and compare these authors' results with our own results, and we'll talk more about that later. So for the first term paper, we did cover COVID sentiment analysis, where the data set was the consist of 72,000 tweets, and the models that were used in this term paper are here. And support vector machine, perceptron, passive aggressive logistic regression had all accuracy more than 98%, and they outperformed other boost which achieved 73% of general accuracy, overall accuracy. Second paper was that regarding the similar topic that we had here. So it is the Twitter sentiment analysis, where the decision tree outperformed KNN and naive Bayes. Decision tree had the overall accuracy of 84% and outperformed KNN and naive Bayes with the 50 and 64%. Third paper was the support vector machine classifier on different data sets. 2 data sets were self-driving cars, and second one was the Apple products. In the self-driving cars, the precision was 55% precision, recall 59, and F1 57, and Apple products much better regarding the support vector machine, and the results were better than in the first data set. So the precision was the higher than in the precision, recall, and F1 scores were higher in the Apple product than in the self-driving cars. So regarding the fourth, it was the paper is what it was airline tweets, voting classifier outperformed Gaussian naive Bayes. On the fifth term paper, it was the random forest with the 88 accuracy outperformed J48, and naive Bayes maximum entropy and support vector machine. This term paper classified tweets as a good and bad, and accuracy was between 80 and 83%. And last term paper were the challenges that we maybe can have in the future. So it was regarding the term interchangeability and data collection. And we were also focusing, like in this term paper, using Python for sentiment analysis and decision making. So for the data set, we use the data set that is available from the Kaggle on kaggle.com, and the data set structure is available here. So some of the most important features of this data set was the tweet polarity, which was the actual sentiment value of the tweet. So 0, 1, and 2, 0 for the negative, 1 for the positive, and 2 for the neutral. Tweet ID was the unique identifier for the tweet that the user posted. Tweet date was the actual date of when the tweet is posted. Query, if there's a query, there is a query. If there's a no query, then it is assigned no query. Tweet user is the actual user that posted the tweet, and tweet content is the most important part, so actual content of the tweet that is posted by the user. On the right side, we can see workflow diagram. That were the steps that we were doing when making this term paper. So first was data loading and overview. Second one is a class imbalance handling. Then text preprocessing and tokenization. And last part was the sentiment analysis and visualization, and also results of the algorithms that we used. So for the class imbalance handling, when we first started using this data set, we saw that the number of negative sentiments was much bigger than the number of positive sentiments. So by using the NLP library and using the downsampling strategy, we saw that previously we saw the number of negative is much bigger than the number of positives. So on the right side, after applying downsampling strategy, we had the same number of the negative and positive sentiments, so the results could be much better. So regarding the text preprocessing and tokenization, after we downsampled and done everything that was needed, we used Lancaster stemmer, convert all the content of the tweets to the lowercase, remove the HTML elements, and also removing special characters and digits. That was all the pre-processing part and tokenizing to make this more better for pre-processing and tokenization. After that, we decided to do the sentiment analysis and visualization. So we applied here count, and to count the number that the most words are occurring in the positive and negative sentiments. So we on the left side, we have the top 10 word occurrences that are occurring in the positive tweets. So we have their good, they, love, HTTP, quote, you, like, get, thanks, comma are the most occurring words in the positive tweets. On the right side, we have the we have the negative word occurrences that are occurring in the negative tweets. So the most occurring words are they, go, get, work, like, today, want, going, got, and back. So after that, we use the TIFI-IDF, which is a term frequency inverse document frequency vectorizer, and split the data set into 70-30 ratio, which is the 70% was going to the training and 30% was going to the testing sets. And after that, we proceed with choosing the algorithms that we talked previously. So we chose some algorithms that were previously used by the other authors and compared our results with those results by the other authors. And the colleague Mirza will later talk more about this machine learning part.
So yeah, now you'll hear from me. Thank you, first of all, for all of you for being here. As you can see here, here's the table of our results. There are certain colors which I'll explain in a bit. I'd like to walk you through some interesting results and findings from our research and discuss a little bit about it. I'm going to focus on how well these various classifiers we used across our research managed to perform. So for starters, I will tell you some numbers. The linear SVC model, as you can see here, initially looked very promising with a high training accuracy at 90%, but this didn't later on entirely translate to a new data, where it dropped to 77%, as you can see here in the testing accuracy. While it performed well in learning from the initial data, it struggled with the new samples. This case happened often with other algorithms. For example, you see here naive Bayes achieved 86% accuracy in training data, but also dropped 77 on the testing set. Then similarly, passive-aggressive classifier, you can see here as PAC, and the perceptron, which is the last one in this table, both achieved 87% accuracy in training, but their testing performance fell to around 72%. To put some context in these numbers, these models gave us a, should we say, false positive in terms of their effectiveness. They seem to handle the training data very well, but then when asked to generalize, their performance dropped. The exception to this was logistic regression, marked here in green, which maintained an accuracy of 83% in training and 78% in testing. This balanced performance suggests that this logistic regression handles both train and test data well. Another case worth noting is multinomial naive Bayes. It managed 85% in training, but dropped to 76% on testing set. And finally, SGD classifier and the Bernoulli naive Bayes maintained a fairly similar accuracies around 76 and 77% in both training and testing, indicating a simpler and, should I say, less advanced learning capacity. So now, to put some context, then what do these results mean? So when models such as, for example, linear SVC, passive-aggressive classifier, or perceptron perform significantly better on training data than on testing data, it raises concerns about possible overfitting. We see this with linear SVC, for example, where the 90% training accuracy looked very promising at first, but then it dropped 77% on testing data, which indicated it may be a little bit too fine-tuned to the specific details in the training set. This practice is often noted in the literature as well, which I'm also going to talk about a little bit more. But on the other hand, we have underfitting case, which may be happening with the SGD classifier, since, as you can see here, it scored around 76.7% in both training and testing. This model might be a little bit too simplistic for our research and to capture all complexities in general sentiment patterns. Underfitting is equally important problem as overfitting, in my opinion, even though it is talked a little bit less about. Here in the green, logistic regression really stands out because it shows a more, should I say, consistent performance, achieving, as mentioned before, 83% in training and 78% in testing. The smaller margin between training and testing accuracy tells us that logistic regression performed the best out of all other models for this research, which was, in one hand, surprising, but in the other hand isn't, because logistic regression is like one of the first and most popular classifiers when it comes to natural language processing between these traditional ones. So now, I mean, these findings that we got align with the trends we observed in the literature on this and other similar topics. Research often shows that high training accuracy does not always guarantee a high performance on a new data we tested. So our results underscores this, and also highlighting the need for model stability in sentiment analysis field, especially when applied in real-world scenarios, which is very important because in those cases, data is constantly changing and updating. And why does this all actually matter? So achieving high accuracy in training data is, of course, I mean, satisfying. Everyone loves it when its model is performing good in training, but it's only half or one part of the job. For sentiment analysis to be useful, should I say, in fields like, for example, customer feedback or social media monitoring or any kind of monitoring or certain financial news analysis, it's crucial that model can perform well, not only on familiar data, but also on new unseen examples, since I said that in the real world, data is constantly refreshing and updating. So we can conclude that generalization is key. And to wrap up, the results emphasize an important takeaway for anyone working in sentiment analysis field and in natural language processing field. It is essential to build a model that strikes a balance between training accuracy and generalization. So training accuracy and testing accuracy. This balance can make a big difference when deploying models in a real world, where data can be very, very often unpredictable. And that is one of the main challenges. So thank you all for your attention, and I look forward to hearing from you.
Thank you, Doctor. It was a great presentation.
Thank you.
Thank you.
Is there any questions from forum?
It's a great presentation. Thank you.
Thank you very
Thank you.
much.